The presentation will be delivered by two people, actually. Myself and my colleague Hayo Hendrikse. Maybe he left already, no?
I'm here.
All right. When we were preparing this presentation, we were thinking, okay, what type of presentation would people enjoy here? Since the presentation is given within the Isaac Newton Institute, and also I looked at what David Abrahams was doing and which chair he guides, we thought, okay, let's try to do it in the style of those people, more or less. So to look across the physics and not only, and maybe a bit of mathematics, not only focus on the phenomenon. So that's what we are going to try to do today. So the contents is long. Most important, of course, here are the pictures. But what I will talk about is how we got to work with this phenomenon. Then it was also very interesting for me. I remember how this all started. And then we had a meeting of what the industry called a meeting of experts, and we couldn't find the way to speak the same language, although it was English, but we definitely meant completely different things with one of the same words. So therefore I will try to define what we mean. And then we will compare, I will make a statement that the ice-induced vibrations and frequency lock-in we are going to talk about is a self-excited phenomenon. I'll explain what it is. I'll remind you basically what kind of other phenomena are of the same type. And then I'll go into a comparison with vortex-induced vibrations of this. Try to show what's similar, what's really different. And then I will come to stage and he will show that how based on all those generic considerations we did choose our path to describe really their ice-induced vibrations of structures, right? That is the plan. So our first encounter with ice-induced vibrations was much later than that for many people here. It was associated with this platform, which is near Sakhalin, right? Of course, it is close to Japan, but it's also close to Russia, right? Once upon a time, we were said that actually this huge platform, and I don't know if you envisage the size, but let's say each leg is in the order of 15 meters in diameter, so it's a big thing. And if you apparently, once upon a time, people sitting in the offices there saw this. And they thought maybe it's an earthquake, maybe it's something else. But I think you would agree with me that's not a good working condition, right? So, and that was apparently related to ice. Then we want to know what it is, and of course it was very difficult to get something from Gazprom, Dimitri. But there are some other ways to get pictures from Russia, so that's how it was obtained. This is a view from the top, actually, of that platform as to how the ice crushes on it. You see, it's a very complex process. Important thing, though, is that in this case, the structure obviously doesn't shake. So I personally don't have a movie which shows how that structure as a whole shakes. Therefore, people in, well, of course, some people in this room know what it is, but this is relatively recent test in HSVA in Hamburg, which shows how a structure that is free to vibrate in this direction is pulled through ice. And now you see that it moves with a relatively low speed. That's not a blackout, it will come back, it's just different speed. And you see that starting from some velocity, the structure starts to shake. That's what people call frequency locking, and that occurs at specific speeds of motion of the structure. And that's what we are going to focus on today in our discussion. So, in actual fact, people know about this already for quite some time, and even in the international standards, there is a paragraph where there is a sort of definition of what kind of ice structure interaction processes can exist. At low speeds, they call it an intermittent crushing. Basically, it means that the ice comes to the structure, fails, the structure vibrates a little bit, and that's it. Then the process repeats. The most interesting one in the middle one, when the structure, as you saw in the movie, sort of shakes in a way which appears periodic. So that's actually what we want to discuss today. And the first question, I think, for everybody who likes physics and mathematics, the first question is, where do you put this phenomenon? In which context? Is this resonance or instability? It's also obviously dynamics. I remember Def and I some 15 years ago, 10 years ago, discussing what is it. At the end, I understood that we mean different things for these words. Is it a synchronization of a sort? Is it similar to a known engineering phenomenon, maybe? So that's the first type of thinking we have about this, to answer these questions. So then, of course, people did measure something in the past. For example, one can take this specific measurements. It's in dry, so you have a structure over there, and you have ice which is pulled towards the structure. And the only thing I would like you to see here is that over a large interval of strain rates, basically velocities of motion of the ice, the frequency of vibration of the structure remains constant. This is quite atypical for force-induced vibrations and very typical for what we call self-excited vibrations. So we tend to call it self-excited vibrations, but before we go into discussion of how and what, it is very clear to me that we need to give a definition so that we understand one and the same thing. To my big surprise, actually, you can find a very good definition even on the Wikipedia. The self-excited vibrations as a term was introduced somewhere in the 1930s. And it is important that it is a periodic motion. It can be also quasi-periodic, so it's not sinusoidal necessarily. Excited and maintained by a source of power that lacks any corresponding periodicity. That is very important. So what is it? It can be ice moving with a constant speed, right? It can be a flow of air, can be flow of water, can be pedestrian crowd walking with a constant speed. Doesn't matter. This is all a source of power lacking any inherent periodicity. Okay, and in that, the self-excited vibrations are different from forced and parametrically excited vibrations, which have to be modulated. That's why we call it self-excited vibrations. You see examples here, of which you all know, right? Also, Erland in the morning mentioned friction-induced vibrations, right? That's one of those. If you would pull a piece of ice over the other one on some kind of a flexible cord, it would shake, right? This is also self-excited vibration in my view, because if you pull it with a constant speed, the source of power lacks any apparent periodicity, right? So it's a brakes wheel, hunting oscillation in railway wheels, shimmy of aircraft landing gears, vortex-induced vibration of chimneys, marine pipelines, human-induced vibrations, whatever. Well, what to choose to compare, because we wanted to compare with something, we decided to compare with vortex-induced vibrations. You will see why, but the other reason is that we also work for quite a long time with those. So this is the vortex-induced vibration. So now I want to compare it. So what is a vortex-induced vibration? You put a cylinder in a flow, and it starts to vibrate. So this phenomena is much better studied than ice-induced vibrations. So what happens is that first there is a flow, no apparent periodicity. Then the flow separates around the cylinder. Vortices are being shed in antiphase, which gives a periodic lift force, which of course, when the period of this force corresponds to one of the natural frequencies, starts to move their cylinder across the flow, and then the cylinder starts to change the vorticity. That's how it goes. Now, is it similar or potentially similar to ice-induced vibrations? That's what I'm going to talk about. Well, what do we know about ice-induced vibrations? I will run them together, and in a way, although I cannot prove it, but to me it seems quite similar. Structure, right? Structure vibrates somehow, both, right? So there is a initially uniform motion. Something happens here that's not really vortices, but some messy stuff. So it seems to be quite okay, right? Now, of course, this is a joke a little bit, but what do we take as a basis of comparison? What is a basis of comparison? And here I would like to be quite serious, because from my point of view, especially for the modeling, it is very important to choose basically what you want from the model. What should it be able to describe? So we know already that power supply is more or less similar, so no apparent periodicity in it. Then we can imagine, and we can make also experiments such that you put a cylinder in a flow, don't let it move, so make it stationary, subject to the flow of water or ice, measure the force, and compare whether these forces are similar to some extent. Second, it's a second type of experiment, also kinematically excited. So the same arrangement, but you move the cylinder with a given amplitude and given frequency. See what the forces are still. Third, self-excitation, so flow and the cylinder which can move. And then the phenomenological models. What I call phenomenological models are not really models which are physics-based, but which reproduce a phenomenon. Yeah, I will explain what it is. Okay, what do we know about the VIV in terms of action on a stationary cylinder? So we know that it experiences a very much periodic lift force. A very much periodic lift force, so across the flow. Is it the same for ice? Well, there are still, I know some people in the ice research community who say, yes, it is periodic. We do think that it's not really periodic. So already here we start doubting whether we need at all to compare it. Maybe it's quite dissimilar. Then, the other very important thing, this movie is actually running. What I want to say is that in vortex-induced vibrations, if you measure the vortex shedding along the length of the cylinder, the vortices are shed in phase. We call it a spatial synchronization. The spatial synchronization is very apparent over there. Is that the same for ice? Yes, in actual fact, especially for low velocities, we know that the ice can spatially correlate, the ice loads can spatially correlate along their contact area. We know that. But is the correlation also present in vibrations? That remains to be seen. Well, then I think quite an ingenious explanation for vortex-induced vibrations was given some 40 or 50 years ago by Professor Sarkaya. He basically did what he calls a forced vibration experiment. So he did put the cylinder in a flow, vibrated it across the flow with given amplitude and given frequency, measured the force, extracted the force in phase with acceleration and in phase with velocity, called the first one added mass, second added damping, all physical, and did plot it as a function of their so-called reduced velocity, dimensionless parameter, and amplitude of vibrations. The main thing he found is that the added mass can be negative, of water, and the added damping in certain areas is negative as well. So he explained the vortex-induced vibrations as a process in which their power supply, the water, creates conditions for added negative damping and negative eddy mass, importantly. Is it the same for ice? We didn't know. We didn't find any research on that topic when we were thinking in this manner. Then free vibrations, self-excitations. Well, that looks, as I said already, very good. So in vortex-induced vibrations, we have a large region in which the frequency of vibration is constant, as well as in ice-induced vibrations. That's obvious similarity here. So very good, similar. Now, the models. So since we had these mixed feelings about similarity between ice-induced vibrations and vortex-induced vibrations, we still had a hope that something can be used. So we looked into their type of simple mathematical models for vortex-induced vibrations. And, well, they basically, the first people who wrote those, they explain it like this. When you have a cylinder and a flow and the vortex-induced street, the von Karman street, this von Karman street goes up and down. They write it as if it was a fishtail. And this fishtail they model with the help of this second-order differential equation in which this Q can be given their meaning, for example, of the dimensionless lift force on the non-moving cylinder. If you look at the equation, what you see here, it's just an oscillator with negative damping for small velocities of vibrations or small amplitudes, which turns into the positive damping when the velocity or displacement grows. There are two equations which do it almost equally well. The Rayleigh equation and Van der Pol equation. Well, you can guess, right, what we choose in Holland. Huh? We choose for Van der Pol, of course, right, because he's a local Dutch guy. Yeah. All right. I wouldn't know any other reason not to use Rayleigh equation, to be honest. But now it is now serious, to be serious. Can we use it actually for vortex-induced vibrations? Because these Van der Pol equations, they actually assume, and if you look at it, that this is the whole, you can imagine Q is a lift force. It's a total lift force on the cylinder. And this equation predicts it to be sinusoidal, really sinusoidal when the cylinder doesn't move. Is this really applicable for us? The answer is no. It is not applicable, and how I will show it very clearly, right? It's close to it, but not applicable. So we cannot do with just one Van der Pol oscillator. By the way, people later, after these seminal works, they come up with better equations, they say, but this one says, you can see, those who do dynamical systems can clearly see that here you have two limit cycles, why we don't measure it, neither in VIV nor in INV, so these, in my view, are not better models. All right, so what do we take away, basically, by thinking across these two phenomena? So we think that when we basically started to model ice-induced vibrations, of which Hayo will talk, that VIV is a nonlinear synchronization process, self-excited process, in which the frequency of their vortex shedding locks on the natural frequency of a structure, and that is very similar, we think, in ice-induced vibrations. Now, so vortex-induced vibrations is enabled by hydrodynamic force that provides effective negative damping and negative added mass. Is this true for ice-induced vibrations? We didn't know, and therefore Hayo took part in the experiments in which this was attempted to be measured. The synchronization takes place of the forces, not only in time, but also in space along the cylinder in VIV and along the contact area in ice-induced vibrations. So similar, but you will see that in ice-induced vibration it takes place to much less extent, much less extent. Why is this? Is it important? That we also can talk. And then it is very, very specific that a periodic load on a stationary cylinder, which we know ice produces, and only partial spatial synchronization along the contact area, they both call for a significantly different, that's our view, from VIV mathematical model. And I think at this point I would invite Hayo to go on with that very model. For you at least it should work from the beginning.
Yeah, I'm lucky. So thanks, Andrei, for the nice introduction to what was my PhD thesis when I started 6 years ago. Now I finally understand where you wanted us to go. So I will talk to you about forced vibration experiments we did, the model we made, numerical model for ice-induced vibrations, and then we look a little bit in more detail to the frequency lock-in in ice. This probably won't work, will it? Oh, nice. This is 2011, more or less. We started with an experimental campaign in the ice basin in Hamburg. This is a picture of the ice basin. It's, for those of you who've never been in an ice basin, a large swimming pool in which you can freeze the top layer in a controlled manner. This is in Hamburg, part of the European Hydrolab project. It's not 7, but I forgot to change the number. And for this experiment, we had one ice sheet, one testing day, so everything needed to be perfect that day. And as most of you who test in ice know, that's almost never the case. So the test setup for us, here we see a sketch of the structure, and this is a picture actually. So we had a beam with, at the bottom, where the ice is a cylinder mounted, that's here, with a pressure sensor, and then some bracing to make it as rigid as possible. We need a rigid structure for this forced vibration test, as Andrei explains. And then at the top we had an actuator and here a hinge, so we could control the motion of the structure while pushing it through the ice. So the controlled oscillation is this one, and what you see here is the harmonic part, where we control the amplitude and the frequency. And then this is the displacement as a result of the constant indentation. So you can do two things. You can push the ice towards the structure and then shake the structure, in which case this term would not be here. But in this basin we actually push the structure through the ice. So we have to add the constant velocity term there. It is in a way the ice drift velocity.
What is the diameter and ice thickness?
Diameter and ice thickness, so that's a long time ago. 200 millimeters diameter. 200, I think, yeah. And the thickness of the ice must have been in the range of 50 millimeters, but I can check for you. 50, 50. So we had, of course, we had one ice sheet, so we had the possibilities to test several combinations of drift velocities in the range between 10 and 100 millimeters per second. Amplitude of oscillation, 11 to 66 millimeters, and in hindsight, that's a large amplitude. When we see the free vibration experiments, amplitudes are usually much smaller. So if we could do it again, I would go for smaller amplitudes. And we had a frequency range of 0.15 to 1.5 hertz. That was dictated by the assumption or not the assumption, we wanted to have a relative velocity between ice and structure which was never negative. So the ice should always be in contact with the structure. And that way we tested 40 combinations. So here is a movie of one of those tests. So we are shaking the structure in a controlled manner, and at some point we will start pushing it through the ice. And here you see an excerpt of the pressures locally measured at the interface. And this we then did 40 times, and then the experiment was over. So let's look into what did we actually see, what did we actually measure. Here you see on the left a plot of the global ice load, so that's the total force on the structure versus time, and on the right the controlled harmonic oscillation of the structure versus time. So when we look at the load pattern, we see that it's actually quite periodic. There are clear, when we start at point A here, we have between A and B an interval where there are multiple failures. These are local crushing failures of the ice, if you wish. And then at point B something happens, the ice load increases to a much higher level, and at point C the ice fails, and this process repeats itself. The peaks, of course, fluctuate, but it's a repetitive pattern. And actually what's interesting there is this temporary stop. So at point B, something happens with the ice, which stops the local fracture process and actually allows the ice load to build up to a much higher level. Now if we look at the relative velocity here, that's actually in the range where the relative velocity between ice and structure starts to become very small. So we enter maybe this ductile behavior range of the ice. Of course, 20 millimeters per second is a bit high for that, but especially here in the range where we are in the order of a millimeter per second, this might play a role. Now this is just the global load, but when we look at the contact area, and these are a lot of pictures, so at the left we see for the same test time versus total contact area. And contact area is measured as the sum of all the points on this pressure sensor which registered pressure at that time. And we see a similar trend, so it's a repetitive pattern again, periodic, and at point B something happens which causes the area to increase significantly. If we look at some distinct images of the pressure, so point A, start there, right after a big failure event, we see we have pressures only at local spots. Not even a complete line-like pressure. It's something we've seen in this test. Of course, a lot of people always criticize the tactile sensor measurements, but it's interesting to keep in mind that ice is not pushing the structure at all over the width at the same time always. Then when we are at point B, here we see that the contact has expanded already significantly. We get some zones with higher pressure, and then going through to point C, we have a much larger area and several zones where the pressure is at the maximum. And then what actually happens at point C is that one of those zones, in this case I believe it was this one, it reaches the peak strength, fracture occurs, and then after that one fails, all the other ones fail, sort of a cascading failure. So it doesn't fail all at once, it fails locally at several positions, and then the structure pushes through the ice. Now to compare point C, which is the sort of the global maximum, with point B, which is more a local maximum in the brittle range, we see that here we have less contact area and also only one spot with high pressure. So there's an indication that some kind of spatial synchronization has taken place here. Then, and this is something I think I have to explain. So what we look at now are this range between B and C. What's going on there which causes this high global loads to develop? And what we see here are several plots, and there I plot on the horizontal axis I call it the ductile behavior time. So that's actually the interval in which the relative velocity is very small, below a certain threshold velocity, for which we say that this process of contact area increase and spatial synchronization can take place. And on the vertical axis we see the peak global load, which develops after that at the end of that interval, the contact pressure and the contact area. And what you can see is that we need a minimal amount of time to actually register any increase in the global load. So if I go back 2 slides here, we need a minimum amount of time here for the load to increase above these levels between A and B. So that shows that something is going on in the ice, which is a time-dependent process, or maybe deformation-dependent process in this case. If you try to estimate this time during which the relative velocity is below a certain threshold, you see 2 things: that it's dependent on the frequency of oscillation. So a higher frequency gives a smaller amount of time, which means you will see less increase in global loads. And that's something, I need some water, that's something which can explain why we never see frequency lock-in or ice-induced vibrations for structures with high natural frequencies. And that's particularly different from VIV, because for VIV we can get frequency lock-in at high natural frequencies, but here for ice that's not really observed often. So it could be that there's not enough time for this whole process to develop at high frequencies. And we also see that the velocity is in there, which means that at high velocities, high ice drift velocities, we also would never observe this type of interaction. Of course, we did these tests to calculate added mass and added damping of the ice, and Andrei has shown these nice plots, contour plots, where we had on the horizontal axis the velocity and on the vertical axis amplitude of oscillation. Now, we didn't have enough ice sheets, we had only one, available to populate such a plot. So in our case, we only have one sort of horizontal line in the contour plot. But what we found within a reasonable margin of error is that the added mass, depending on velocity, shows a decreasing trend, and then either becomes a little bit negative or zero, but I think we cannot draw a conclusion yet. But for the added damping, the trend was quite clear that we have very negative added damping, and then it approaches the zero value for higher velocities. So when compared to vortex-induced vibrations, it seems to be that the ice-induced vibrations, the lock-in is a consequence of negative added damping only, and not both negative added damping and negative added mass. So modeling, because we did these experiments and then the aim was to make a model out of this. And what we concluded is that we need a model which contains multiple individual contact zones. We need to be able to model this local contact process and increase of contact area and synchronization along the contact area. So we need multiple zones. We need to be able to model local failure. The elements have to be able to fail locally. And we need somehow to incorporate this process where the contact area expands at low relative velocities, which we thought is a delayed local failure at low velocities, resulting in a synchronization. So the approach in terms of modeling is my, well, I wouldn't say famous yet, but often criticized for being so simple model, but it works. So on the left you see our representation, a top view. So we have a structure, it could be a cylinder or a rectangle in a way. It's a 1D model, so it doesn't matter yet. I will get to the 2D implementation later. And what we do is we split up the ice in n different ice elements, completely uncorrelated individual elements. These can be next to each other or on top of each other, but they are not interacting. For each ice element, we introduce this representation, which contains elastic component, and the arrow indicates that we take into account fracture at a certain deformation limit in that one. Then we have an anelastic component, recoverable, and here we have included the dashboard later to model the power law creep. Of course, in a very simplistic manner. And for the structure, this is the most simple approximation we can use, a simple oscillator. Of course, when we do modeling of real structures, we include multi-degree of freedom systems, but for analysis of the problem, it's not really necessary to include those details. So the equation of motion for the structure is very simple, oscillator with an excitation of the ice. The ice force is the sum of all the ice elements in contact with the structure. For each ice element, we have 2 degrees of freedom. The equation is given here, very nice. We see the 3 of the power law creep. And what we do is we say, as soon as there's a certain strain in the front spring or certain deformation, the ice element fails. At that moment, we remove it and we place it with a certain offset with respect to the structure, which we draw from a uniform distribution. Now, this is not physical in a way. We don't know if a uniform distribution makes sense, but we don't have enough data yet to support any other distribution, and it seems to work. All right, so what does it do? This is a movie. When we look at the top left, that's a rigid structure, so a structure which cannot move in the ice. And then here you see the force at the bottom left, which is aperiodic, and the colors indicate local stresses in a way. So this, of course, the distance between ice and structure is exaggerated, but you see all these local points hitting the structure, interacting with it, coming into contact with it. Now, if we place a structure in that ice which is allowed to freely move, what we see is that actually the elements start to synchronize. So here we start with a random ice sheet, ice edge, and then as the structure moves away from the ice, all the points synchronize and we reach the peak stress here, and then you have this cascade of failures. So what's actually happening is that as soon as the structure starts to move forward, when the ice pushes it, the relative velocity between ice and structure goes down, it reduces. And when it reduces, we saw that this contact area can start to expand. And in this case, it reduces so much that the whole front of the ice can come into contact with the structure before one of the elements reaches its critical strength and fails. That's what we see in intermittent crushing, so this is really this sawtooth behavior. Now, when we look at frequency lock-in, it's also an old movie, but similar setup. Is this frequency lock-in actually? Oh yeah, here we go. What we see is that the ice doesn't synchronize over the entire width necessarily, resulting in these oscillations, this harmonic oscillation pattern. So, well, this actually synchronizes quite a bit, but trust me, it doesn't always. So that's actually very nice. So with this model based on this forced vibration experiment, which says that the contact area can expand if you load ice slowly, we can actually simulate these interaction events for flexible structures. Now when we look into this lock-in in more detail, the lines are not very visible unfortunately, but here we see on the left structural displacement versus time, which is the typical close to harmonic signal at the natural frequency of the structure, and on the right we see a typical ice load pattern, which shows this repetitiveness we also saw in our experiments. Now, two questions maybe for discussion later. We see there is a partial spatial synchronization in this contact zone, but is there truly a temporal synchronization going on? Because after each big failure event, the ice has a quasi-random ice edge again, new points come in. So the situation is more or less has seen a reset. So it's not that the frequency of oscillation, there's a frequency in ice which is synchronizing with the structure, frequency of the structure. Therefore also the question is frequency lock-in, which to me implies that both systems have a distinct frequency which somehow lock into each other. Is it actually a good name for this? That's something we can discuss maybe. Some other details which are perhaps interesting in comparison with VIV. Here we have the ice velocity on the horizontal axis and the structural response on the vertical axis. The lock-in range, as already found by Toyama and others in 1983, and many other people after them in experiments. In the lock-in range, the amplitude of oscillation shows a more or less linear dependence on the structural velocity. So on the ice velocity. So as the ice velocity increases, the amplitude of oscillations grows as well. So the most critical one for design would then be the maximum velocity in this case, where your amplitudes are biggest. This is not the case in VIV. Another thing we often see is that here we have ice velocity and frequency, that the frequency or the observed frequency of oscillation of the structure is a bit below the natural frequency of the structure. It's a bit tricky where this comes from. I think the origin is that at the moment the structure wants to move back towards the ice slowly delays its motion because it doesn't feel exactly at that moment the structure wants to move back. So it resists the structure a little bit, causes a small deviation from the purely harmonic signal. You can imagine that when you have a pure harmonic signal, you go like this, and then right at that point you want to go back, but when you're resisted to go back, you sort of start to deviate a little bit, which we see mainly at the lower velocities, and could be explained by our positive added mass in this case. Then some nice figures. This is a phase plane, so displacement of the structure versus velocity. In lock-in it's a car tire maybe, but you see that there's clearly a limit cycle. It is almost a circle, but there is a certain band. The amplitude of the structure is always changing from cycle to cycle, and that's to balance out the power input and the power output. So for our model we have a viscous dissipation mechanism, so the power out is the red line very small, and the input from the ice in one cycle is sometimes it's a bit more, sometimes it's a bit less, because there is a natural randomness in the process, of course. The last thing which is for me was interesting to see in comparison with vortex-induced vibrations. For vortex-induced vibrations, we have the through-off frequency, so the frequency of vortex shedding, increasing with velocity. Hence, if we put a structure with a natural frequency of 1 Hertz in a flow of 1 meter per second, it will start to interact. If we increase the frequency to 10 Hertz, the flow velocity needs to increase as well to make sure to maintain the interaction. And what we see in this case is that if we increase our frequency, the lock-in actually occurs at lower velocities. Now the question why comes back to this interaction time which is needed, this minimal time which is needed to generate this increase in contact area. A higher frequency means you have less time. You have less time for this deformation process to take place, to develop. So at a higher frequency, you need to compensate with a lower velocity. I showed the formula before. This I didn't do. Oh, sorry. So that's the animations I copied. To conclude, for ice-induced vibrations, it is self-excited. We say it's driven by partial temporary and spatial, temporal it should be, and spatial synchronization of the ice load with the structural motion. It is enabled by the ice force, which in this case provides negative damping, negative added mass. We don't know yet. I think it's not the case. When we look at the numerical model, we don't see negative added mass, but we need more experiments to confirm that. And the important thing actually is that the synchronization requires an interval of time during which the relative velocity between the ice and structure is small, smaller than a certain threshold value. This comes down to moving towards the range of rates or velocities where the transition from ductile to brittle behavior takes place. Then open challenges, and there are many, which is a good thing, can keep me busy for years, but I would like some friends to work with, so please guys. Studies into, well, in terms of the model, stability of the limit cycle, we are looking into the effects of initial conditions on the development of the vibrations. It's of particular importance in designing structures and also in interpreting data, full-scale data, for example. The transition, when does this sawtooth happen, and then at what velocity does this change to this lock-in and then to this random process? That's a very important thing. I mean, for design, it's what we actually want to know, but we are studying that. And one thing we've been looking into, but not with great success yet, is if we can identify some dimensionless parameters as is common in other fields. Then for model development, well, do we actually require more accurate or more in-depth modeling of the contact zone? As I said, we have completely independent elements. There's no correlation, uniform distribution. There's no experimental evidence that is at all true, but it seems to work for the global behavior. Of course, by looking into in more detail, we can actually start linking the model parameters to physical ice parameters. So that might be necessary, and that's actually the point there. This is phenomenological model. We made a model which can reproduce what we saw, but then the question is always, how do you link that with the physical processes and parameters there? And we need that in order to be able to scale results. Then for experimental work, yeah, we want to test some extremes and some validation. We did some validation studies in Hamburg. I didn't show them for reasons of time, where we've shown that the model can predict your interaction for a flexible structure, but we did not yet obtain the sawtooth range, so we have to confirm that. Acknowledgements, always important. So we have our partners in the Samkot project, which is a very big project in Norway, and they actually fund all our work, and what we do mostly is look into engineering problems, mainly at the moment for offshore wind turbines in the Baltic Sea and Bohai Bay near China. where we simulate the interaction between ice, wind turbine, and also we have the aeroelastic loading. So it's quite an interesting phenomenon to model. And now we have a picture of TU Delft. Thank you.
Oh, yes, please. Thank you, Hayo. Andrei. If I understand correctly, the load that you see from B to C, about a factor of 2 increase.
Yeah.
And you're suggesting that that's associated with the contact area changing
Yeah.
by about a factor of 2, maybe?
Less. A little bit
So-
less, because the pressure also redistributes. So I can go to now.
So what I'm getting at is you've imparted a strain of the order perhaps of unity, 0.5, 1, somewhere that. How much time elapsed from B to C? How much time?
Well, in this case, less than a second.
Less than a second.
Yeah.
Let's say a second.
Yeah.
That would imply roughly that you're imparting a strain of 1 per second, strain rate. Now a critic could argue that that rate of strain is far too high for ductile behavior. On the other hand, another critic could argue quite the opposite. You're putting enough strain of the order of 1, is far more than enough to dynamically recrystallize the ice. And according to my rough calculation here, one could expect the new grains to be, of micron, 10, 20 micrometers in diameter. And if the ductile to brittle transition truly scales in a way that we've proposed over the years as 1 over grain size to the 3 halves, you could well be, within those fine grains, ductile. So even though the rate of strain might be the order of 1 or more per second, and the critic could say, sorry, it's brittle, your answer would be no, not necessarily so.
I like the second
Thank you.
critic.
Thank you.
Yeah.
Yeah, just want to get a clarification. When you calculate all these negative damping and negative mass, what assumptions are you making? I mean, is it you assume a sinusoidal oscillation per se, and then calculate this thing? How do you do that?
We measured the displacement of the structure but we controlled it, but we also measured it just to be sure that it didn't deviate too much, of course, from the expected controlled oscillation. And then we take the first harmonic, so the coefficient in the Fourier series, and also from the ice load. Yeah.
Okay.
So we assume indeed, but that's the procedure for calculating added damping.
So it doesn't contain the complete force, of
No,
course.
no.
So we have quite a random force signal, and we more or less represent it as a Fourier series, and the added mass and added damping corresponds to the first terms in the Fourier series.
My second question is that when you calculate this relative velocity with respect to the ice, you're not taking the deflection or the compliance of the structure itself. It's the imposed velocity is the only thing that you're considering in your presentation.
Yeah, I think we've talked about this.
I don't think we understand the question, to be honest.
No, I think we do, but the structure.
Okay, we do.
You mean the elasticity of the beam, right?
That's correct.
Yeah. See. So we actually measured the it's not shown here by laser the displacement at the ice action point, which includes this elasticity. So in a way it is in there, but I know in our original paper it was not mentioned like that. But by measuring the actual displacement at the ice action point, you include this.
That's right. And in your paper, did you present that measurement, or was it just mentioned that it was like that? I mean, but in your,
I don't remember because I know the review of that paper. Perhaps now I also know the reviewer, and I don't know what we did in the updated version. But we did take that measurement into account in the calculation of the added damping.
Yeah, nice talk. I like the piece of work. Couple questions. Was that model ice or just freshwater ice? What kind of ice was in the tank?
Model ice, yeah.
How,
HSVA.
where they use like CO2 or urea or I don't know what they
It's
use.
not urea. I always forget.
It's a saline.
Oh, it is. It is.
Yeah.
So it's not model. It's actually saline.
Weak and
Very weak.
yeah, very weak.
Saw it in the movie, right?
Okay, and the other thing is, have you looked at the ice? Are you able to arrest this process? I won't say arbitrarily, but at some maybe try a few cases where you arrest the process and just go in and cut the ice out and look at the damage.
No, we didn't do that, unfortunately.
Because from my line of thinking, that I've seen, actually it was years ago watching some of Dev's experiments at the lab. It was kind of an unusual process, but in freshwater ice where you can see the cracking really well, you'd have this close-in damage zone with the grain refinement, but actually where the failure would take place is away from that, because that's somewhat confined at the interface, very strong because of the small grain size, but then the actual pop that had caused that big drop in stress occurred away from the interface a bit, like outside of that damage zone. So I wonder if you do continue, it strikes me as you might get some, since you are, and I like that line of thought, but you're thinking of getting more into the physical side of things, you might consider those kind of observations to inform how you enhance your ice model. So I think there could be some periodicity in that process that would kind of fit in your
Yeah,
analysis.
for sure. We don't want to say that everything happens in the interface. Not at all.
Good, yeah, nice, well, thank you.
Question, because you had the 5 centimeter thickness ice. I didn't see your experiment, but I saw a similar experiment very recently in Ari. And it was clear visible that ice edge behind of indented oscillate because some wave transfer energy from the region of interaction. Do you think that it may add some hydrodynamic effects into the consideration?
It may. But we do know that the ice-induced vibrations can occur without that as well. That we know for certain.
Yeah, but did you see electrical gravity waves in your experiment?
I don't remember in this
Not
one.
very visible.
but-
They were there, of course.
They
You
should
cannot
be there.
avoid those.
Yeah.
That's impossible to avoid. But those ones were much smaller than those you refer to, I think. Because in the last HSVA ones, it's
Yeah, the
really
ice
this.
is exactly.
Yeah, but that was not the case.
No. They're of course smaller, but since they are excited, so then they change contact area.
They may, but we do think, likewise, Erland also saying that probably the effect of this is not too big. That's our opinion.
We have 2 minutes, so I have 2 questions.
Okay.
Yeah, very simple. First of all, your ice looks like it's not solid ice. It's more like viscoelastic, non-Newtonian fluid, or at least granular fluid. So then it could be, CFD or something can be used to simulate that. And but then, if it's non-Newtonian but still fluid, so there are more reasons to speak about the analogy with vortex-induced vibration. And in particular, what you showed about vortex-induced vibration, you showed so-called cross-flow vibration. But you didn't show inline vibration. But for ice, it's only inline vibration. So my question is, did you observe cross-flow, cross-motion vibration? No. So that
Also, the structure was
could be, yeah.
Well, but that's maybe because of the setup. Because
Yeah,
I
the
would
setup
I would
would
not
not allow
say
it
that
either.
that it doesn't happen at all.
Yeah,
I think it
because
does.
because it could be that ice goes on both sides of the cylinder, so there's no space I mean, it's
Yeah,
restricted, so it can.
It's confined.
Yeah, it's confined. Yeah, so there is a difference. It's
No,
not-
we are well thinking of this quite a lot as well, because it can be also friction induced maybe.
Yeah.
But we didn't find any significant evidence as yet of this.
Okay.
along this-
Okay, we have two more questions. Yeah.
Along
Hi.
this line, just to continue on with this discussion, I do not agree with you that it's a self-excited vibration, because it is in the direction of the ice movement. You're forcing the structure to deflect out, and then when it fails, it comes back, and then it does that. So in that way, I think it is not self-excited, it is forced vibration. But besides, I think I'll stop there.
Yeah, and very short, please. Yeah.
No, the question that I was going to ask is about the ice conditions itself, the temperature, modulus of elasticity, because I guess in general, model ice doesn't fail in the same way in compression as full-scale ice. So just what if you characterize the ice itself?
I have the data for you. Not here anymore, but I used to once, so I can share it. But we did typical temperature, salinity, compressive density, everything. Yeah, we often get the comment that this is model ice and it's not real ice. It doesn't look like real ice and it doesn't behave like real ice. So what are you doing? But the interaction and the results we see from the structural perspective are the same as we see in full scale. So yeah. I think it's still worth investigating it this way.
Please do note, Def and I do disagree on this definition for more than 10 years. So there are many self-excited vibrations which happen in the same direction as the flow. In the morning, Erland was speaking about one of those, for example.
Yep. Okay, thank you very much. And we have 30 minutes for afternoon tea, by the way. And after that, we have another presentation from our chairman. Please come in 30 minutes, and thank you very much.